This video marks a rather significant moment in our discussion of set theory, since what we're going to do today is give a set theoretic definition of what the natural numbers are. And in fact, we're going to see that we can define up the natural numbers in terms of operations on the empty set. And after we do that, we're going to talk about the notion of induction and what an inductive set is. And it'll turn out that these two ideas, one being the set of all the natural numbers and the notion of an inductive set, these two ideas are going to be very intimately connected. One of the themes in axiomatic set theory is that every single mathematical object that we talk about is really just a special sort of set. And one example that we've seen so far is we've defined up the ordered pair as a special sort of set, namely using the Kuratowski definition. And the same theme is going to hold true for natural numbers. And indeed, we want to say that numbers are just a special sort of set. So what we're going to do is we're going to claim that the natural numbers can be given a set theoretic representation, and that the symbols that we just use, like 1, 2, 3, 4, these are just shorthand notations for a special sort of set. And as I said before, we define up an ordered pair such as 1, 2 using these symbols as just a special sort of set, namely the set containing two elements, the first element being the set containing 1, and the second element the set containing 1, 2. And furthermore, if you take another ordered pair, we're just using this notation as a shorthand for something like this, the set containing 1. And what I want to do today is to give a set theoretic description of the natural numbers. And what we want to do is we want to take objects that we assume to exist in the set theoretic universe. And I use the word atoms for this, and this is a term that's been appearing all through set theory and all of analytic philosophy, where we say that atoms are the basic building blocks in your analysis of mathematical objects. So what we want to do is take the atoms and build up more complicated objects, such as natural numbers. So in the set theoretic universe, what are these atoms? Or a similar question would be, what would be the minimal number of atoms that we have to suppose in order to construct interesting mathematical objects? Well, I claim that if we grant the existence of just the empty set as an atom, and the truth of the ZFC axioms, and by the way, you might want to review these ZFC axioms in my second video, especially if we grant the truth of the power set axiom, and we'll see later if we grant the truth of the subset axiom, we can start to build up interesting mathematical objects like natural numbers. So let's construct natural numbers. So all of this is really the work of people like Zermelo and von Neumann. So what they did is that if you start with the empty set, in our set theoretic universe, we only have one atom so far. So let's call the number 0 just the empty set. We're going to say that 0 is indeed the empty set. So since we have one atom so far, just the empty set, let's stick that atom into another set. And what we're going to do is we're going to take the next number after 0, which we're going to use the symbol 1 for that. We're going to say that's the set containing 0. And you can see that if I define it that way, then 1, the symbol 1, is just a set containing the empty set. So now I have really two objects in my universe so far. I have 0 and I have 1. So let's define up the symbol 2 to be the set containing both of those objects, the set containing both 0 and 1. And you can see if I define it up that way, 0 is just the empty set. And from my previous definition, 1 is the set containing the empty set. So the second member of the set 2 is just going to be the set containing the empty set. So hopefully you can see the pattern that we're starting to form here, where we're recursively defining the next natural number in terms of ones that have already been defined. So you can see the pattern here with 0, 1, and 2 is once I've defined 0, I can define up 1, and then I can define up the number 2. So just following that pattern, the number 3 would just be the set containing 0, 1, and 2. And this is legitimate because I've already defined up what 0 means, what 1 means, and what 2 means. So to write it out in terms of all these empty sets, 3 is going to have 3 elements. And you might start to see that this sounds semicircular, but remember that I can always paraphrase number 3 as, I can always say something like this symbol 3 is really just this set. I don't have to refer to the notion of counting. I don't have to refer to the notion of threeness or anything like that. So this would be the representation of 3 in terms of those empty sets. And hopefully you can see the pattern by now. So if I wanted to continue to define what 4 is, I could just say it's the set containing both of 0, 1, 2, and 3. And for higher numbers like 10, this is going to be the set containing all the natural numbers that I've defined so far, namely 0 through 9. So just to give you a piece of history, this whole thing that we've done with defining up the natural numbers in terms of empty sets and sets containing empty sets and so far is the von Neumann construction of the integers. And we would say that 0, 1, 2, and 3 are examples of von Neumann integers. And I think Zermelo was the one who actually did this, but for some reason this whole construction that we've just done is attributed to von Neumann. And if you're interested, it's actually very much related to the notion of a von Neumann universe, where you build universes of sets on top of ones that already exist using things like the power set axiom. And just as a piece of notation, you may have seen elsewhere that the empty set is just written either as this O symbol with a dash through it, or sometimes it's written as just two curly braces with nothing in them. And I use this one just because I think it's more aesthetically pleasing, and I think this one's illegible. But just so you know, you'll see both of those. So if I just use that symbolism, then the number 3, we said before, is given this representation with the empty set. But if you just write the empty set as those two curly braces next to one another, then this whole thing would actually be the number 3. But I think this is kind of repulsive, so I choose to write it like this. One thing I also wanted to point out in our discussion is that this is how we're going to define the natural numbers so that they can be usefully incorporated into foundational mathematics and within set theory. But you may have also noticed that what we've done doesn't really answer any philosophical questions of what number is or what quantity is, or what is, as Bertrand Russell would say, what is the two-ness about the number 2, or what exactly does 2 mean, or where is the number 2. So our goal for today is just to give a useful definition of natural numbers so that they can be incorporated into set theory. So let's formalize our notion of a number being after another number. And what we're going to call that is the successor of a number. So what we're doing before is we defined up the number 0, and then we said that 1 was, in a sense, after 0. And what we did is we used definitions of 0 to form a definition for 1. So what I'm going to say is that if I have some number a, then the successor of that number, which is going to be denoted by a plus, is the following. So if I have some set a, the successor a plus is going to be as follows. A plus, the successor, is going to be a union with the set containing a. And just to make that clear, what we're going to say is that the successor of 2, so 2 plus, is going to be equal to 2 union the set containing 2. And from before, we saw that we defined 2 as a set containing 0 and 1. So we're going to union the set containing 0 and 1 with the set containing 2. So that means that the successor of 2 is the set containing 0, 1, and 2. And then, of course, we gave the symbol 3 to mean the successor of 2. So 3 is going to be equal to 0, 1, 2. So this is just a symbolic form of what we've been doing all along. And hopefully one thing I can share with you in this video is that once we grant the existence of the empty set and the notion of succession, we can speak of all these other numbers like 2, 3 as successors of the empty set. So we can say that what 1 really is just the first successor of the empty set. We can say that 2 is 2 successors of the empty set. 3 would be 3 successors, and so on. So in fact, if you really want to, we didn't have to use these symbols at all, like 1, 2, and 3. We could just say empty set and successor. But this is, again, this is a repulsive notation, because if you have like 20, you don't want empty set 20 pluses after it. So of course we have symbols like 20 to do that job in set theory. And one other thing I'd like to share with you is that if you grant the existence of some number a, or I should say some set a, then a plus also exists by the Z of C axioms. In other words, if I grant the existence of a, then this operation that is performed here is legitimate, and it guarantees the existence of another set called a plus. And I leave that as an exercise for you guys to show. Basically what I'm saying is that using axioms like, let's say union axiom or power set axiom or pairing axiom, if I grant the existence of a, what follows from that is the existence of A+. So next I'd like to talk about the idea of induction. And I'm going to introduce a definition, namely, some set A is said to be inductive if and only if the empty set is within the set A, and for all the objects A within the set A, then the successor of A is also in the set A. So just to put that into symbols, that A is inductive if and only if the empty set is in A, and for all the A's that are in the set A, the successor of little a is going to be in the set A. Alright, so this probably looks pretty familiar with something you may have experienced with inductive proofs in your other mathematical experiences. Now you can see immediately that such an inductive set is going to have infinitely many elements. Why is that? Because we're saying that in order for A to be inductive, first the empty set has to be within A, and then for all the A's in A, the successor must also be in A. So if I say that this statement is true, that the empty set is in A, then the successor of the empty set has to be in A, and then again, if this is true, the successor has to be in A, and I get this infinite chain of inferences, where as soon as I grant this, and if I still want to retain that property of induction, then all of the successors have to also be in A. So I have infinitely many elements. So, is there any way to justify a set with infinitely many elements? Can I just collect infinitely many objects and stick them into a set? And it turns out that in order to justify this rigorously, you can't prove this from the other ZFC axioms that we've introduced so far. So what I'm going to do is introduce another ZFC axiom, namely the axiom of infinity. And this is very straightforward. It's just saying that this property that I wanted here, the axiom of infinity is going to declare that there exists an inductive set. So basically, with this property of induction, the axiom is just going to say that there exists some set A that has this property, such that the empty set is in A, and that for all elements in A, the successor is also in A. So the axiom of infinity is just declaring that there is at least one inductive set out there in the set theoretic universe. As I'm going to claim, the natural numbers are intimately tied to the notion of induction and succession. And one thing I'd like to do as well is I'd like to give a definition for a natural number in general. What I did in the second slide was I gave a definition of symbols like 2 as being the set containing 0 and 1, or I've defined what 3 is, but I haven't said what a natural number is in general, or how to spot a natural number if presented with one. So we're going to define a natural number as a set which belongs to every inductive set. So another interpretation of that is, if I give you some inductive set, then I can say that a natural number is indeed in that set, and the natural number is going to be in every single inductive set that's out there. And this leads to a theorem which I'd like to prove, that there exists a set which I'm going to denote as omega, which contains exactly the natural numbers, meaning that it has only the natural numbers and it has no other elements in it, just the natural numbers. And as you can see, this set omega is going to be the set of natural numbers. So the proof is going to run as follows. So by the axiom of infinity, there's at least one such inductive set. There's one set out there in the universe which has the property of induction. And I'm going to call it big A. Now by the subset axiom, and this is why I suggested that you review the subset axiom. So by the subset axiom, there's a subset of A, which we're going to call omega, such that omega has a property of being in A, has a property that all its elements are within A, and that X is in all inductive sets. And why did I form this proposition? Because this set omega is guaranteed to exist by the subset axiom. Because remember what the subset axiom is. It's just saying that the X's are going to be in A, and some proposition involving the members of this set. And I can plop in any proposition I want here, and I just choose that proposition to be X is in all inductive sets. So you can see that if I take these two claims, X is in A, by the way, A is an inductive set, and X is in all inductive sets, then the second claim, X is in all inductive sets, is a much stronger claim than X is in A. So that means that this AND statement really reduces to one statement, that X is in all inductive sets. And as an analogy for that, let's say I had two declarations here. I had X is a cat and X is a mammal. Now, which of those two declarations is stronger? It would be X is a cat. Which is because all cats are mammals. So if I grant the truth of X being a cat, then it just follows that X is also a mammal, because all cats are mammals. So you can reduce these two declarations into the stronger one, the more restrictive one. So omega is going to be the set whose members are in all inductive sets. And you can see from the definition of natural number, it's going to follow that all the elements of X are going to be natural numbers. So what we conclude from that is that omega contains the natural numbers and only the natural numbers. There's no extra stuff in this set. And it's actually not too hard to show from this is that the set of natural numbers is itself inductive, and it's a subset of all inductive sets. So this is a pretty big moment in our set theory discussion. We've basically shown that the set containing all natural numbers exists from one of the ZFC axioms. I'm going to now introduce a very important mathematical idea, which is called the induction principle for the set of natural numbers omega. And this inductive principle declares that any inductive subset of the natural numbers is itself the natural numbers, which means that if I have the existence of the natural numbers, and here it is right here, that if I try to take any subset, and if that subset is going to retain the property of induction, then that subset must be all of the natural numbers. And just to make that intuition clear, let's try to find a subset of the natural numbers which is still inductive. And let's call that set big A. So in order for big A to be inductive, just by the meaning of the word inductive, the empty set has got to be within A. And furthermore, this chain of inferences must also be true, that if the empty set is in A, then the successor of the empty set has to be in A, and the successor of the successor of A of the empty set has to be within A, and so forth. So now just collecting all the stuff that has to be within A in order for A to be both a subset of omega and inductive, we can see that I have to collect all of the elements of omega. And if I decide to trim off any part of omega, like let's say I make the subset of omega just a number 0 through 10, then that subset, it's a subset of omega, but it's not inductive anymore, because the successor of 10 wouldn't be within that subset. So in order to create an inductive subset of omega, I have to include all of omega. I can't just trim down omega. And hopefully you notice that these are the two steps that are commonly done when you prove something by induction. You want to say that the empty set, or 0, is in that set, and that this chain of reasoning will hold. Namely that if you say that some object, I chose the empty set here, but if some object is in A, then the successor of that object has to also be within A. And that's basically verifying that chain of reasoning here. So what you're showing is that if these two propositions are true, that if the empty set is within A, and if this chain of reasoning holds, then that subset you've created is all of the natural numbers. It's not just some of the natural numbers like 0 through 10, it's all of the natural numbers. I'd like to now show you the inductive principle in action by proving a theorem. So the theorem is going to be that every natural number except 0 is a successor to some other natural number. And notice that in this theorem, I'm making a claim about every single natural number, that every natural number has the property that it's either 0 or it's the successor to some other natural number. So the strategy for this proof by induction, and it's a proof by induction because I'm showing that this property holds for every single natural number, for infinitely many numbers. So what I'm going to do is I'm going to create a set which is going to list out all the natural numbers which have this property of either being 0 or they're a successor to some natural number, meaning that they follow some natural number. And we're going to claim that this set is in fact all of omega, that's equal to omega, and we're going to show this by induction. So there's the theorem again. So the way to prove is, like I said, I'm going to construct the set A, which has as its objects x, and the x's are going to be, they're all going to be natural numbers. And the objects within the set A are going to have the property of either being equal to 0, or there's another y value within A, such that the x serves as a successor to y. And this is just what it's saying verbally, that x is a successor to y. And this whole proposition is just a symbolic form of what the theorem is saying. And one thing I'd like to point out is this exclusive or. So that means that either this statement, that x is equal to 0, or this statement is true, but not both. And if you do any computer science or electrical engineering, I'm sure you'll have seen the XOR before. Now, I'd like to first point out that this set A is guaranteed to exist by the subset axiom, and that's because omega is guaranteed to exist. And what I'm doing here is I'm saying x is in omega and some other proposition involving the x's. So this set A could conceivably be the empty set. It could be true of no natural numbers, or it could be true of all natural numbers. In fact, I want to claim it's true of all natural numbers. So the set does exist by the subset axiom. So first I'd like to show that the empty set is in A. So we want to show that the set A is inductive. So is the empty set, is that in A? And hopefully you can see that it is, because the empty set is a natural number. And the empty set is indeed equal to the empty set. So it satisfies both this proposition and that proposition. So that means the empty set gets to be within the set A. So indeed the empty set is within A. So that's the first step. And then the second step is to show that if I assume the truth of some natural number k being within A, then does it follow that k plus is also in A? And it turns out that's true as well, because if I assume that k is in the set A, then there is indeed a y in A. Remember, there exists a y within A, such that the successor of k, k plus, is equal to y plus. And remember that I'm trying to show that this x could be equal to k plus. And in order for that to be true, there has to be a y within A, such that x, or k plus, is equal to y plus. And what is that y, such that k plus is equal to y plus? It's in fact equal to k by assumption, because k is guaranteed to be within A. And indeed, k plus is equal to k plus. So we've shown that this chain of inferences, that k being in A implies that k plus is in A, is always going to be true. So what we've shown is that A is an inductive subset of the natural numbers. And by the principle of induction, this inductive subset of the natural numbers is equal to the natural numbers. So the set of all the natural numbers having this property right here, that they're either 0 or the successor to some other natural number, is true of all the natural numbers. And that wraps up this video. And hopefully you've gained some appreciation for how induction can be used to prove theorems which make a statement about all the natural numbers, and how they follow from the Z of C axioms. And here are the practice problems for this lecture. And if you enjoyed this video, feel free to subscribe, check out my other videos, and stay tuned for the next video.